Welcome. This video will present a brief introduction and overview of STREAMLINE, an open-source automated machine learning tool developed by the URBS-Lab. First off, STREAMLINE stands for Simple, Transparent, End-to-End Automated Machine Learning Pipeline. Simple here refers to being easy to use by those with and without coding or machine learning experience. Transparent refers to the pipeline being clearly defined and providing extensive output to users at every step. End-to-end refers to the fact that STREAMLINE fully automates all generalizable machine learning pipeline elements that can be reliably automated without specific problem domain knowledge. These elements include exploratory data analysis, both before and after data processing including basic data cleaning, basic feature engineering, and data partitioning. Also feature processing, including missing value imputation, scaling, pre-modeling feature importance estimation, and feature selection. Then modeling itself, including 16 scikit-learn compatible machine learning algorithms, as well as hyperparameter optimization, model feature importance estimation, and model evaluation with 16 standard classification metrics. Also post-analysis, including analysis summaries, statistical comparisons, figure generation, organization of output files, and saving models for future use. Also comparing datasets. Specifically, when more than one dataset is run within STREAMLINE at once, pipeline performance is automatically compared across the multiple datasets. And if replication data is available, STREAMLINE can automatically re-evaluate all models on that further holdout data in order to more ideally pick a best performing model. And lastly, the generation of a summary report, in this case as a formatted PDF that includes key findings. We'll begin by taking a look at a simplified schematic of the STREAMLINE automated pipeline, which is made up of 9 sequential phases. The first phase is data exploration and processing, including initial exploratory data analysis, basic data cleaning, basic feature engineering, a secondary exploratory data analysis of the processed data, and k-fold cross-validation partitioning of the data into training and testing sets. Phase 2 involves imputation and scaling of the respective data partitions. Phase 3 involves feature importance estimation using 2 fast and complementary algorithms. Phase 4 involves feature selection, adopting a collective feature selection approach. Phase 5 involves all aspects of machine learning modeling, utilizing up to 16 built-in scikit-learn compatible algorithms, automated hyperparameter optimization, training an optimized final model for each algorithm, model feature importance estimation, and model performance evaluation. Phase 6 conducts a number of post-analysis steps, including data summary and figure generation. Phase 7 optionally allows comparison of multiple datasets being run within STREAMLINE at once. Phase 8 involves replication data re-evaluation of all trained models. And Phase 9 generates a PDF summary report conveniently documenting and organizing pipeline settings as well as key findings. The STREAMLINE automated pipeline was designed to adopt best practices in data science and machine learning analysis, as well as deal with common data challenges with specific emphasis on biomedical data analysis, and to be able to scale to larger data analysis given sufficient computing resources. It was also designed to detect and interpret complex associations, for example, multivariate feature interactions, and to include reliable default run parameters so that it could be easily used as is by non-experts, as well as allow flexible customization and ongoing future expansion. And ultimately, it was designed to empower anyone to easily explore, train, compare, interpret, and apply a variety of predictive machine learning models as part of a rigorous and optionally customizable data mining analysis. Regarding logistics, STREAMLINE is programmed using Python 3, along with many common libraries including pandas and scikit-learn. Open source code along with detailed documentation can be found at the following links. STREAMLINE also comes equipped with multiple run modes for flexibility and accessibility for users with and without any coding or machine learning experience. The simplest run mode is within a Google Collaboratory notebook, which requires neither coding nor coding environment setup. The next simplest run mode is within Jupyter Notebook, requiring only coding environment setup. STREAMLINE can also be run from the command line, with run parameters specified either within a configuration file or via command line arguments. The pipeline's also set up to run one phase at a time or across all 9 phases with a single command. From the command line, STREAMLINE can be run locally with or without CPU parallelization, and it can be run with high-performance computing parallelization currently across 7 different types of DASC-compatible CPU clusters. Some of the key limitations of STREAMLINE as of version 0.3.4 include that it is currently only set up to handle binary classification tasks. However, we expect to complete expansion to multi-class and regression tasks in the near future, so keep an eye on our GitHub repository. Additionally, STREAMLINE is set up to only handle structured tabular data. And like other AutoML solutions, any problem-specific data cleaning and feature engineering is up to the user prior to running STREAMLINE. STREAMLINE differs from other automated machine learning solutions in that it follows a carefully designed, transparent, and standardized pipeline workflow. This is in contrast to conducting a meta-algorithm search of pipeline configurations, which can be very computationally expensive, as well as different from focusing on extensive user-driven pipeline customization, which makes STREAMLINE easier to use and helps to avoid common pitfalls, mistakes, and biases. STREAMLINE also rigorously applies and directly compares a variety of established and cutting-edge machine learning modeling algorithms. It automatically generates and organizes figures, visualizations, results, and analysis summaries for each phase of the pipeline. Furthermore, STREAMLINE is among the minority of automated machine learning solutions that automates exploratory data analysis, basic data cleaning, or outputting separately trained models for each cross-validation partition, which is important to directly assessing the potential impact of sample bias in data partitioning. STREAMLINE is believed to be unique in its ability to automatically analyze and compare multiple datasets directly, or to engineer binary missingness features in order to determine the predictive value of data entries that are missing not at random. It also utilizes cutting-edge methodologies that are particularly well suited to bioinformatics or biomedical data, such as multisurf and turf, both relief-based feature selection algorithms, the collective feature selection strategy, and extracts, a rule-based algorithm designed specifically to address the challenges of detecting and characterizing epistasis and heterogeneous associations in biomedical data. It's also unique in its ability to automatically conduct statistical significance comparisons between algorithms and datasets, as well as compare and contrast feature importance estimates across modeling algorithms, and generate a comprehensive shareable summary report and ensure replication data is processed appropriately for each model. As mentioned, STREAMLINE automatically generates a variety of figures and visualizations. These include exploratory data analysis figures, illustrating class imbalance, visualizing significant univariate associations, and visualizing feature correlations. Also, summarizing ranked feature importance estimates, visualizing performance in hyperparameter sweeps during modeling, and in post-analysis it generates summary ROC and PRC plots, as well as feature importance box plots, and a unique composite feature importance plot summarizing feature importance estimates across all machine learning algorithms together. It also generates data comparison plots, summarizing data and algorithm performance differences across the STREAMLINE run, and with the help of included useful notebooks, it can also generate direct visualizations of decision tree and genetic programming models as completely interpretable solutions. And lastly, it generates PDF summary reports, documenting pipeline run parameters, summarizing key findings, and displaying key visualizations. STREAMLINE has many potential target uses. For example, comparing the performance of different machine learning algorithms on a given dataset. Notably, STREAMLINE also includes the ability for users to fairly easily add other scikit-compatible machine learning modeling algorithms to its repertoire. So researchers that have developed their own machine learning algorithms can easily add and benchmark their method to a variety of other standard machine learning algorithms. Also, as mentioned, STREAMLINE can be used to compare machine learning performance across multiple target datasets. For example, datasets that include different feature subsets, or datasets that include or don't include covariates in order to examine covariate impact on modeling performance. Another key use of Streamline is being able to easily apply any model that's trained to other future data, for example, replication data. And we envision Streamline to be useful as a baseline of comparison to evaluate other automated machine learning tools, given its direct, pre-configured, and consistent pipeline design. Furthermore, Streamline could serve as an educational resource for those who wish to design their own custom machine learning analysis pipeline, or to get a better idea as to how a variety of standard data science packages and tools can be used as part of a pipeline. The Streamline code comes set up to run on demonstration data in order to illustrate the pipeline in action, as well as to help users confirm that it's running as expected before applying their own data. The demonstration includes a hepatocellular carcinoma survival dataset taken from the UCI repository. This dataset represents a biomedical binary classification task, including 165 instances and 49 features. This dataset exemplifies many of the basic data challenges, including having mixed feature types of both categorical and numeric, missing data values at around 10%, and class imbalance with 63 deceased instances and 102 instances that survived after 1 year. The demo also includes a customized version of this dataset designed explicitly to test and confirm the functionality of Streamline automated data processing. The easiest way to run the demo is through Google Colab by navigating to the link at the bottom of the page or scanning this QR code. This can even be run on your phone. Once you've opened the link, click on the 3 lines representing the menu, and then select Runtime, and lastly, select Run All. This demo should take about 6 or 7 minutes to run. As mentioned, Streamline also comes with a set of useful Jupyter notebooks, allowing you to do even more with the Streamline output files. For example, with these notebooks, you can regenerate key plots based on user specifications. You can also report model prediction probabilities for testing and replication dataset instances. You can examine the impact of decision thresholds beyond the default 0.5. You can run a complete training data evaluation of all models rather than just outputting the standard testing evaluation. And you can generate additional figures, including a feature importance ranked heat map, and as mentioned, direct visualizations of decision tree and genetic programming models. As a brief note on the history of Streamline, it originated with an implementation called AutoML Pipe BC, which was a simple and pre-configured pipeline setup in a Jupyter notebook. You can view an early preprint applying this notebook to a study of pancreatic cancer at the following archive link. The first published release of Streamline, version 0.2.4, can be obtained at the following link and pairs with this manuscript published in 2023. This manuscript can also be viewed as a preprint at this link on archive. The current release of Streamline, version 0.3.4, as of December 2023, is available at the following link and pairs with a preprint applying this new release to an investigation of obstructive sleep apnea across an international cohort. The archive link for this paper is also given here. Furthermore, over the last couple of years, a handful of other publications have applied various earlier releases of Streamline to study various biomedical outcomes, including cognitive outcomes, Alzheimer's disease, acute respiratory failure, and cancer patient readmission. Streamline has become a pillar of our lab's research program, and we're actively working to expand its capabilities and improve its performance further. The most important improvement in the works is to expand its applicability to multi-class and regression tasks. We're also working on integrating direct support for cloud computing parallelization, and incorporate new explicit feature interaction characterization tools, incorporate ensemble modeling options, and the automated comparison of ensembles to baseline models, as well as strategies to facilitate model deployment for making predictions on individual future instances, while also providing prediction interpretation and explanation. Some of the other expansions we're working on include adding other machine learning modeling algorithms to Streamline's repertoire, incorporating outlier assessments into the exploratory data analysis, incorporating Shapley values as an alternative model feature importance estimation approach, expansion of the repertoire of pre-modeling feature importance estimation algorithms to go beyond the 2 currently included, extending the repertoire of missing data imputation strategies, and incorporating additional visualizations of data and results. To conclude, here's a detailed schematic of the current STREAMLINE AutoML pipeline. Be sure to check out our video providing a detailed walkthrough of this pipeline to better understand how it works, as well as some of the key design decisions. Thanks for listening to this brief overview of STREAMLINE automated machine learning. Please feel free to reach out if you're interested in collaborating or you have any questions.